today it's easy to introduce or not introduce Greg. We all know Greg, we all love him. But let me give you a little bit of biographical information about him. He did his undergraduate degree in Illinois, Urbana-Champaign. Then he went to Stewart Observatory in the University of Arizona, where he got his PhD in 2001, but actually didn't get it in Arizona. He moved with his advisor, Hans Walter Rix. You have to ask Greg to say it in proper German accent. He moved to Heidelberg, to the Max Planck Institute of Astronomy, where Hans Walter Rix became the director. Then he moved, he stayed in Max Planck Institute in Garching, and he was a postdoc with Simon White. Then he moved back to Arizona to the NOAO in Tucson for Neil Goldberg, postdoctoral fellow. Then he came here. Right? Yeah. I think that's what's written here, must be true. Another thing that I want to mention is what Greg wrote on the board here, and he's going to give a public talk on Thursday evening, 7 o'clock, the Pine Room at the Kansas Union, and the title of this talk is, The Evolution of Galaxies Over the Last 10 Billion Years. It'll be a cool talk. Come and see it. Great.
Thank you. So it's very nice to be able to give this talk. I was gone last year, so some of you may not recognize me. That's where I said the when not in Germany. I was on sabbatical in Germany for a year. And so I'm going to talk a little bit today about the general ideas of galaxy evolution, the specific area I work on, highlighting some of the stuff I worked on when I was in Germany, and then kind of giving some future projects that we're starting now, that we're kind of built up momentum then, that will carry us through for the next few years. The main science question that I deal with in astronomy is nature versus nurture, right? Are things affected by the places in which they live, things being galaxies in this case, or are their properties kind of set by something intrinsic? And so as an example of this, taken from my experience in Germany, nature versus nurture, just because you live in Germany doesn't mean you end up liking beer. That's my kid. This is Oktoberfest. He did not like that beer. So, there are things that are intrinsic to people, and there are things that are not intrinsic that are nurtured phenomena. And so I'm going to talk about how we can test this in galaxies. Now, some of you Chris Fisher started this theme of showing pictures of his kids drinking beer when he came back from sabbatical from Germany, so I just thought it'd be good to continue the tradition of my child drinking. That's actually lemonade mixed with beer, but it doesn't really matter.
Don't put that online.
No, I won't put that online. It's apple juice. Okay. So when we study galaxies, we do it against this backdrop paradigm of galaxy formation that starts from when galaxies were not in existence, but when all the matter in the universe existed in a nearly completely smooth bath. And that is echoed in the all-sky picture here of the cosmic density, it's of the temperature of the universe, of the gas of the universe, around 380,000 years after the Big Bang, when the universe recombined from ionized to neutral hydrogen and became transparent. And that radiation free streamed through the universe for the last 13.7-ish billion years, until photons from there or there or there, 13.7 billion light years away, happen to get to our telescopes. When we see them, we see a snapshot of the universe as it looked like a few 100,000 years after its start. And this is an image from Planck. It's an all-sky map where the Milky Way has been subtracted out. And these little wiggles are 10 to the minus 5 density fluctuations of the universe of those early times. We can start from that early, very smooth, but not completely smooth density distribution and try and understand the buildup of structure in the universe and the buildup of galaxies in the universe, primarily, at least for much of the matter, through the force of gravity. This is a simulation of how that smooth density bath grows under the force of gravity for a box that's about 65 million light years across. And so this network of filaments here are what happens as the matter starts collapsing because of the initial gravitational instabilities and collapses into this rich filamentary structure we call the cosmic web. This number here gives the time since the Big Bang, and while that matter, which is mostly dark matter that makes up most of the mass in the universe but is invisible and doesn't interact with radiation and has, if anything, a very small interaction cross-section, self-interaction cross-section, as that collapses, the gas in the universe also collapses into the same filaments. The temperature is what's coded here by the colors, and you can see at the nodes of these filaments, like right there and right there, the gas heats up. Some of this is as the gas falls in and is shock heated to the virial temperature of those dark matter concentrations or halos. Some of it is from energy put in by feedback from gas as it spirals into the black hole in the centers of the galaxies and the centers of these halos. And all of these little blue dots right here are where gas is cooled in dense clumps in these halos, and that's where we think galaxies live. So this is a beautiful simulation done by a different collaboration, nothing to do with me. But it's a simulation. It's a model. It puts in what we think are basic recipes for physics, some of them not so basic, and then tries to understand how galaxies evolve within this evolving cosmic web. I'd like to observationally test how this picture works and how galaxies that live maybe there and galaxies that live there differ from one another, and if they're influenced by their environment. Are they influenced from being in this hot gas bath versus being isolated there? So how do galaxies grow in a more descriptive kind of way? Well, we know that dark matter grows by gravitation, and the gas cools from 10 to the 5 to 10 to the 6 degrees into galaxies. It radiatively cools into these dark matter nodes, these what we call halos. When that gas gets to be around 10 to 100 degrees Kelvin and dense, it can start forming stars. And so this is an example of a star-forming region in our own galaxy, the Eagle Nebula. Just for a sense of scale, that's a few light years in size. The solar system would fit in that little nub right there, just for a little sense of scale. And this is a site of star formation in the Milky Way. In this case, it's seen by the Hubble Space Telescope. Now, if you take a bunch of star formation regions like this one, you can look at them in a galaxy-wide context. This is a nearby spiral galaxy, M81, where these pink regions are all individual star-forming regions around an area that's in the center that's quite devoid of them. And so you can have galaxy-wide star formation as this gas cools and forms into clumps and forms stars. Now, star formation isn't just a one-way process. When stars turn on, they heat up the gas around them, and when they blow up, they blow out the gas around them. And if you have a galaxy like this one, M82, a nearby star-bursting galaxy, that combination of radiative input and kinetic and thermal input from the explosions can actually blow the gas out of the galaxy en masse. And you see that dramatically here. In the center of this galaxy are tons of exploding stars, and they drive a wind, which is seen in this cone. This is hydrogen gas emitting from the n equals 3 to 2 transition in a hydrogen atom. And you can also see, if you look in different wavelengths, dense molecular gas and dust being blown out here as well. So galaxies can self-regulate by putting energy back and heating the very gas from which they survive. Galaxies can grow from this self-regulated in situ process, but they can also grow via mergers. So for example, these are the antenna galaxy, a nearby pair of merging galaxies. And when two galaxies merge together, a few things happen. First of all, the stars in those galaxies get added together to the same bunch. And then the gas that was in those galaxies that was going around them, and these were like Milky Way-like galaxies before they merged, that gas can get torqued and exchange orbital angular momentum of the galaxies with the angular momentum of the gas. That gas, once it slows down, can funnel to the center and drive vigorous starbursts. In this case, there's a huge amount of star formation buried beneath this dark stuff there, which is dust. And by dust, it's kind of like the soot, candle soot, right, that you get. It's dark silicates and sometimes carbonaceous grains. For soot, it's not silicates, but the dust in the interstellar medium is silicates, carbonaceous grains that can block light. So galaxies can grow this way. They can also grow if you take two galaxies that merge that have no gas in them, aren't forming stars and merge together. They just grow by their stellar components. So we can try and track this process over time in mass. This is something I did back in 2003, one of the very first measurements to do this, again in 2006. Lots and lots of people have done it since then, as shown in this really nice compilation by Piero Madao and Mark Dickinson, where we can map the stellar mass density of the universe. That is the amount of stars per cubic megaparsec. A parsec is 3.26 light years. So 1 parsec is 3.26 light years. 1 megaparsec is 3.26 million light years, right? So some volume of space. And you can see that over time, the amount of stars in the universe decreased, as it must have. In the beginning, there was only gas. Now we see stars in the sky. And it's grown by a factor of around 5-ish in the last 11 billion years. We can also ask the question of how do the ages of stars in galaxies change over time? So this is a plot from a paper I did in 2006 where I took all the galaxies in a given volume of space, centered at 4 different redshifts when the universe was 2.3, 3, 4.5, and 7 billion years old. And those red points are actually the sum of all the light at the same rest frame wavelength. So what you would see if you were actually there looking at the galaxies. And the black's a model fit, the blue are model predictions. And what you can see is that as you go to later and later times, the age of the stars that go into this model fit also increases. Right? The stars in the universe are getting older with time, averaged over all galaxies. But that aging is happening at a rate slower than the universe is aging. This is exactly what you'd expect if stars are constantly being made over time. It's not like you made all the stars in the distant past and just let them passively evolve, where no new stars are formed. You actually are adding new stuff to the mix, so it biases the age of your average towards younger ages all the time. What I'd like to know is, given this, can we understand how galaxies evolve? Do they evolve all the same way? Are there different modes of evolution? And to think about that, we should think about, can we somehow split galaxies up into different categories by physical properties to understand how those different groups of galaxies may have evolved? This is a plot of the color of a galaxy, galaxies from the Sloan Digital Sky Survey. There have been many, many versions of this plot. This is just a particularly visually pleasing one. So it's color, where red usually means light is dominated by old evolved stars, and blue means light is dominated by young stars, versus stellar mass. And you can see that there's a bunch of galaxies at red colors, so old ages and high stellar masses, and things at blue with a gap in between. Those green lines are just some notional mapping of where this kind of division is, but it's not obviously a physical one. You can also map the ages of galaxies via spectroscopy. So I'll describe these later, but there are ways you can define the mean age of the stars in the galaxy by using spectral diagnostics of their starlight. And you can see that as you go to high stellar masses, galaxies are dominated by old stellar populations. Right? Notice the axes are flipped here. And at low stellar masses, they're dominated by young stellar populations. So we can isolate galaxies using these different means, and we can study the evolution of these different populations, this older population and this younger population, as a function of time. So this is a paper that we did in 2011 where, let's just look at, these are 3 different mass bins of galaxies. Let's just look at this one here. These are the highest mass ones they looked at, so you can see them farther back in time. And you can see that as you go from a redshift of 2.5 down to 0, when the universe was about 3.5 times smaller than it is now, down to the present day, and there's cosmic time up there, that the mass density in these passive galaxies kept building up, and the mass density in the star-forming galaxies kept dropping, or being constant. And the implication there is that I'm taking stars, I'm forming stars in the star-forming young population, right? So if nothing else happened, they should keep growing and growing as they form more stars, but they don't. They stay constant or decrease, which means that those galaxies must be transitioning, turning off their star formation, and being added to this group of galaxies here that has no star formation. So we interpret this now as this transformation of star-forming galaxies to non-star-forming galaxies via some kind of quenching process of star formation. Now I can say that star formation is quenched over time, but actually to have that work is kind of difficult. So the universe is filled with gas. There's lots of it, and gravity works everywhere. So if all you did, this plot, by the way, is a plot of gas funneling in to galaxies along the same filamentary structure that I showed you earlier. It's from a simulation by Avishai Dekel. And in the absence of any other feedback, that gas would just cool into the galaxies, and the galaxies would all form stars like gangbusters. There would be no red and dead galaxies in the local universe. So if we want to understand how this transformation happens, we have to consider physical things that can prevent this gas from falling in. And there are a host of them. Some of them are intrinsic to galaxies that involve physically blowing the gas out via this feedback from star formation and even feedback from the heated gas that accretes into the central supermassive black hole. There are also models where when the gas falls into halos above a certain mass, that gas gets too hot to cool efficiently. And so the cooling time gets very long, and those galaxies just drop pretty quickly in their star formation rates. I'm not actually going to talk about those. I'm going to focus on the extrinsic modes of ways you can stop star formation, the environmental modes. Although we always have to be conscious that these different ones can both work, and I'll show you the evidence for that in a minute. So you can imagine that galaxies are surrounded by some hot gas reservoir, that cold gas falls in the filaments. When it hits the other gas that's in that galaxy, it can shock heat to the virial temperature. That gas then cools onto the disk. The disk and the bulge of the galaxy grow up at some different rates, and the galaxy gets bigger and bigger with time. Right? So how can we differentiate this kind of, what I talked about, this intrinsic quenching, which again I'm not going to really talk about that much, and this environmental quenching? This is a plot from Peng et al. 2010 where they looked as a function of mass and density of galaxies relative to the mean density of galaxies. Right? So this is the average density of the universe. And the color coding is the fraction of galaxies that are passive. So if you go to a fixed density, let's just pick the mean density. As you go to more and more massive galaxies, they get more and more passive. Right? The color code is the fraction of passive galaxies in each bin of this plot. So that means that no matter what your environment, at high masses, you're always quenched. There's something intrinsic about the galaxy that's doing this. There's a host of research on this. Stephanie Junot talked about some of this very nicely in her colloquium from a few weeks ago, and I don't have time to talk about it more now. At low masses, however, as you go up in a density, you also increase the amount of environmental quenching, And so we interpret that as a separable environmental source of quenching. Right? There's no fixed property of galaxies that you can control for that allows you to reproduce this trend with density. So how did the star formation proceed? How did the shutdown of star formation proceed in these dense environments? And there are a few theoretical mechanisms for this. This is from the same simulation I showed before. This is stars and the way they'd actually look if you observe them, including effects of dust and stellar aging and everything. And this is the gas density. And so you can have mergers of galaxies when you have groups of galaxies where you can have 10 or 100 galaxies in a small area with a low velocity dispersion. They can couple together quite strongly. They can merge. And that gas can get heated up, and you can see sometimes these little puffs happening. That's when gas is about to fall into black holes around these galaxies in the models, gets heated up, and blows out the gas explosively. And you also transform the morphology, the shape of the galaxies as well. You can also cut off the gas supply from which galaxies are fueled. So in this picture before, where galaxies are fueled by these streamers, when a galaxy enters a dense environment, it no longer becomes the recipient of the gas falling into it along these filaments, and it uses the gas in the consumption time scale, which is about 1 to 2.5 billion years. Both of these are affected at this is effective at group mass scales and up. By group, I mean a dark matter halo with a mass of around 10 to the 13 and a half and up. Where these really are only effective in groups, because in clusters, the galaxies are flying so fast by one another that they don't ever actually merge. They just can experience tidal interactions. You can also vigorously strip the gas out. If you fly, clusters are filled with a hot intracluster medium that's 10 million degrees. Galaxies can fly through this with speeds of 1,000 kilometers a second. When that happens, they experience a ram pressure. When that ram pressure exceeds the restoring force of the gas to the disk, it can get stripped out. And you can very rapidly, on the order of one crossing time of the cluster, strip the dense star-forming gas directly out of a galaxy. And models try and incorporate all of these things. Some incorporate just this, some both. All of them have mergers in them. But if you put those kind of recipes into state-of-the-art models of galaxy formation, you find this.
Sorry, Greg, you're saying that the other galaxies coming and just dripping away?
Well, there's, in a cluster of galaxies, which I haven't actually defined yet what a cluster is, but it's thousands of galaxies, halo masses of more than 10 to the 14 and a half solar masses. those velocity dispersions are 600, 700, even 1,000 kilometers a second. When those galaxies fly by each other, they don't merge because they're moving at each other's relative escape velocity. But they can tidally strip some of the stars. The galaxies do experience a tidal kick, but that's not enough to completely shut off star formation. If you look at the models, the red is the model for all galaxies. All these models do pretty well. The models are the lines at high masses. But if you break galaxies up into the centralmost massive galaxy in their halo, what we call creatively centrals, and the galaxies that are outside that central one, which are called satellites, the models do a pretty good well with these central galaxies, where we think this intrinsic quenching mode is most dominant, but they fail dramatically for the satellite galaxies. They way overpredict the efficiency of quenching when they do their best job at putting in these processes. So we need to go through from the observational side and try and understand this a little better. So now what I'm going to do is I'm going to talk about some of the work that I've been doing in this field for the past, really 15 years, but focusing more on the stuff in the past few. I did a lot of this while I was in sabbatical in Germany. One of the places I went to was Hamburg. I got to give nice talks in nice places. This is the Hamburg Library, this really beautiful classical old observatory with 2 stories of books and this sliding ladder and stuff like that. I got to eat lots of delicious cheese, another reason to go and take sabbatical and travel and do research abroad. And I got to get my students into shape by vigorously exercising their minds and their leg muscles. Apparently these jokes aren't funny, but that's okay. But that one was. So what I'm trying to do is use galaxy clusters as a laboratory for understanding these environmental processes. Clusters are the most massive pseudo-virialized objects in the universe. They're actually not virialized at all, but they're the most massive objects that are even close to being in virial equilibrium. And when galaxies fall into clusters, they pass through a range of environments, from kind of low density, which we call creatively the field, through this filamentary structure, through groups, and into the cluster environment. So we can probe a range of different densities by looking at these systems. And I kind of nominally split things up by this mass cuts for this talk, but these cuts are somewhat arbitrary. And at the end, this is just a name, and this is just a name. So don't get too hung up about them. So what I'm first going to talk about is the buildup of passive galaxies and clusters at redshifts less than 0.8. So that's when the universe was 1.8 times smaller than it is now, and when it was about 7 billion years younger than it is now. I'll talk about plans for future studies of clusters that we're now doing as a large observational program at redshifts of 1 to 1.5, with a bunch of clusters there, and then studying how galaxies are falling into clusters and probing them way before they actually enter the cluster environment. So this is a project from something called the this is the plot from something called the ESO Distant Cluster Survey. What we've done is we've isolated these passive galaxies with no star formation, and we've tracked their relative numbers going from bright galaxies, which are more massive ones, to faint galaxies. And you see that as you go from distant galaxies down to nearby galaxies, these are composite luminosity functions for clusters, so many clusters stacked together. And you see that the bright galaxies were basically already there all the way back 7 billion years ago, but that those faint galaxies are building up slowly, right? Well, not slowly, actually quickly over time. And so you tend to, for whatever, this is kind of something that models have to reproduce, right? I don't have an explanation for why this is happening, but the massive galaxies and clusters already have to be there in the distant past. It could be because they were quenched by things that had nothing to do with being in the cluster. They were massive already, something intrinsic quenched their star formation, yet these things down here only got quenched when they fell into the cluster environment. And as these clusters grew in mass, those galaxies got their star formation shut off by one of those processes, and it built up this low mass slope of the luminosity function. And the total amount of passive galaxies and clusters increased by about a factor of 1.5 to 2 over this time period. So that's looking at star formation. I've talked about how we can split between passive and non-passive galaxies. We can also look at different types of galaxies. So we can think about their structure. So you can really think about how galaxies that have a disk-like structure. So these are things that are rotationally dominated. So most of the stuff is going around with a much larger rotational motion than its velocity dispersion. They're star-forming disks. They tend to have blue colors. And they tend to have relatively high gas fractions. 10% of their atoms are in gas. The rest are in stars. Of their atoms, right? Forget dark matter for now, although it's obviously important to understand these. And these are just images of what those kind of galaxies look like. So brighter galaxies here, redder galaxies up here, and you go all the way down to blue galaxies. So actually, if I wanted to compare these, I should have flipped this. I didn't think about that, right? So if I flip this around this axis, this would be basically a one-to-one mapping onto this plane. Now, the reason structure is important is because structure is modified by these processes. When galaxies merge, their structure gets messed up. They can turn from spirals into other kinds of galaxies I'll show in a second. But if they just have their gas stripped out, that doesn't change their stars. Stars don't feel the Ram pressure. The gas does. So by studying the shape of galaxies, the morphology of galaxies, you can understand the nature of the processes that are affecting them. There's also these kinds of galaxies here. These are things where their motions are almost entirely dominated by dispersion, by the random motions of stars. And these are dominantly these red galaxies here. They have no or little star formation. Right? So we can try and isolate subsets of these galaxies, ones that look like this, which we call elliptical galaxies, and ones that have significant disk components, but are still dead galaxies, which we call S0s or lenticulars. It's a historical name. Don't worry exactly where it comes from. You blame Edwin Hubble. So we can chart the numbers, the fractions of galaxies in each of these components in clusters over the last 7 billion years. And so I have the S0 fraction, so it's number of S0s over the total, and a bunch of individual clusters, the spiral fraction, the elliptical fraction, and these two added together. And what you see is, over time, that S0 fraction increases, the spiral fraction decreases, and the elliptical fraction stays constant. Right? And if you actually ask what are the numbers added to clusters of these things, and compare them to the number lost of these things, they exactly match. There's a plot that shows this from another paper, but the plot's really ugly, so I didn't put it up, but just trust me, I can show it to you later. It's just a not very well visualized plot. And so we can see that galaxy morphologies, their shapes are being changed by some process happening in clusters. And we can try and relate this to the star formation history. So I can now show this plot right here, which shows the buildup of the passive galaxies that I talked about. This big buildup right there is happening in that swath of time when the morphologies weren't really changing. And that implication is that whatever is shutting off star formation and changing morphology don't work at the same time. That something is depriving the galaxies of gas, or removing it, shutting off their star formation, and only later do they transform their morphologies. Now, we can try and understand what happens to actually make this. Now start going in individual cases, trying to understand what's actually causing this differential change in the morphologies and the stellar populations. And this is one thing that my student Sinan Der, who's somewhere here, right over there, has been working on, where he measured the actual fraction of galaxies that are merging in these same exact clusters as a function of their environment. So things that are in groups, things that are inside the cluster, things that are kind of in the outskirts of the cluster, and things that are way outside the cluster, so the field. Now, at first, you say there's not much in this plot. It looks relatively flat. But that would be misleading. Right? There's actually something very interesting here, I think, which is that, and these are just, these galaxies have these red points and these blue points are the same clusters, except the red points just have more galaxies but have higher systematic uncertainties. So I'm just showing them both for the purpose of this. Now, clusters are a bad place to merge galaxies. They're moving by each other so fast, they just shouldn't merge. They shouldn't be able to stick, gravitationally speaking. And you have a lot of them. So if I drop galaxies in from the field with this merger fraction, where something like 17% of them are undergoing a merger, and there's a lot of work that went into making this plot, identifying mergers, testing the methods, all the stuff Sinan's doing as part of his PhD research. If you took this number of galaxies here and added it to a cluster where most of your galaxies aren't merging, you would expect this merger fraction to drop as you move into clusters. The denominator gets much bigger, the numerator stays the same. That's not happening, though. It's staying constant. That implies that merging may actually be enhanced as you go into clusters. Now, we haven't tested this by forward modeling the observed signature with models, with simulations, but that's going to be a part of Sinan's thesis. is trying to now take galaxies in simulations, drop them in the cluster, see when they merge, and see whether or not you get this kind of signature and see how it relates to the enhanced merging. We'd also like to understand not just the merging history of the clusters that can modify their shape, but also their star formation histories. And so to do that, we can utilize spectral diagnostics. So this is just an example of two of the ones that we use, or the main ones we use. These are two different models for galaxy stellar populations, so ensemble populations of stars formed in one burst with an age of 500 million years and 2 billion years. And you can make different indices to kind of extract the maximally age-sensitive features from these spectra. For example, you can take the relative flux of two bands here, which we call D4000, and you can plot it over time for a galaxy in black, which is just forming stars constantly, and a galaxy in red, which all of a sudden stops its star formation. And these indices change this index, this ratio of these two quantities, mean fluxes, causes very large differences. This is something, for example, that Donald used a lot in his paper he's writing with me and also for the thing he'll be presenting in his master's thesis on Friday. You can also measure the depth of certain emission lines. The depth of those, absorption lines, with respect to continuum showed here for the same star formation history. One where star formation rate goes constant and one where it drops have very different values. So these give different probes of star formation over different time scales. And we can plot all of the galaxies in our sample for this, again, this sample of clusters at intermediate redshift, where we measure these two quantities, this absorption line strength and this 4,000 angstrom break strength, for different things, for clusters, groups, and field galaxies, where they've been color-coded by how much emission they have from star formation and from other processes. And so what you see, and so just to interpret this, right, these galaxies are all lying on this sequence here. Ignore the magenta lines just for the moment. We can interpret this. This is something that people have known since, I did a paper on this in 2000. People have published lots of stuff on it, that galaxies lie in this plane. And the reason is because if I let models of star formation in galaxies evolve over time, all the tracks of things that form stars continuously lie on this locus. These tick marks are tick marks for 1 billion years apart. So galaxies that are forming stars constantly and never stop, never get out of this upper left corner. Galaxies that exponentially decay their star formation rates with a time scale of 1 billion years are this red curve, and galaxies which form in a burst are this black curve. So you can relatively age date things as younger, intermediate, and older. You can't absolutely age date. That's actually not possible with these indices, but you can do it relatively. And one of the things that we're going to be doing, and something Sinan's going to be doing in this thesis, is actually understanding how these stellar populations, how the relative ages of things and the amount of stars they're forming here match up with their morphology, their merger rates, right? Or so whether a galaxy is merging or not. But one thing we noticed along the way was when we looked at the galaxies, like almost as a side project, which turned into what I think is an interesting paper, is if you actually look at the distribution of these emission line galaxies in different regions of this plot. So let's first of all just look at example spectra of things in different regions. These magenta lines notionally divide up things as older, intermediate, and younger. And that line here is drawn basically where you get a lot more galaxies. That's where kind of in clusters you see all these old galaxies piling up. And if you look at spectrum of these things that are in the younger bin have lots of emission lines shown in blue. They have absorption lines. Those familiar with stellar populations, some of you in the audience will know these are just very classic young stellar populations. These are things in the intermediate bin. Some of these things like the Balmer absorption line that is an indicator of age has gotten weaker. They've gotten older. They still have some emission lines. You have old things which have no emission. These are just what you expect if you take a bunch of stars and have them not have any new stars for a few billion years. And here are those same galaxies, but some subset of them have a small amount of emission. And it's these galaxies here that I think tell us something interesting about the processes that can shut off gas accretion onto galaxies in clusters. So let's just focus on these. And what you see this literally just came out of this when we were looking at the data, and we pursued it in a paper that I submitted to AppJ, is that the fraction of galaxies in this bin of older stellar ages that have emission is different in the different environments, right? So you have to be old to be in this region. It's kind of weird, right? So it's a little complicated. To be in this region, you have to be old. Otherwise, if your stars weren't old, you would be up here. Yet some of these things have emission lines, which normally we associate with hot gas from star formation. Turns out that's probably not the case. Turns out that gas is probably because every star gives off mass. The sun has a solar wind. Any stellar population that you make over the course of its life will return 50% of its mass back to gas by supernova, by winds, by mass loss. And that gas gets heated by the stars already in the galaxy with no new star formation needed. And nearby studies of galaxies have shown, where they really have exquisite spatial maps, which we don't have in the distant universe, show that galaxies with no star formation have these emission lines. And they're co-spatial with the stars, they co-rotate with the stars, and they can be heated by the stellar populations you see. So we think these are old galaxies that are kind of gasping out some gas that can get reheated by the stars in them. We can compare the fractions of these galaxies that are old with emission in different age bins, right? So for those younger two age bins in 3 different environments, the galaxies look basically like they have the same fraction of things with emission. This isn't surprising. We've known this for a while, that when you're in a cluster or a group, and it's one of the many pieces of the puzzle to solve this, that if you're forming stars, you're forming stars. If you're not forming stars, you're not forming stars. But the actual amount of star formation you have is not really sensitive to your environment. And that implies that whatever is cutting off star formation doesn't gently suppress your star formation. It cuts it off like an axe, because you don't see a lot of things in clusters with really suppressed but still ongoing star formation. However, if you're already passive, if you've got these old ages where you don't have any new stars, you see a difference between the field galaxies here and group and cluster galaxies down here. And that implies that something is happening to try and limit the amount of gas in these dead galaxies. Now, you have to go through, kind of explore a lot of possibilities to uncover what's actually causing this process. I'm not going to go into that in this talk. But what we think is happening, I'm not going to give all the background unless you really want it, but what I think is happening is that these old galaxies, when they fall into, every galaxy sits inside of its halo, and it's getting fed by these gas filaments. And even when a galaxy isn't forming stars anymore, it still is exerting a gravitational pull on the gas around it. That gas trickles in and is slowly heated. So every galaxy that's isolated is getting that gas. In addition, galaxies are producing their own gas by stellar mass loss. If you're in the field, right there, you just make your own gas and get new gas. But when you're in a group or cluster, you're cut off from that surrounding gas. You don't get it anymore. And so you only have what you have. And that's enough to kind of produce this difference. And that kicks in even at group scales, right? The signal to noise is not very high because our error bars are large. But it looks like at group scales, already you're sufficient to cut off the accretion of gas. This isn't what's cutting off star formation. These are already dead. But it gives an insight as to what halo mass you need to cut off the gas accretion in galaxies. So 2 remaining questions, which aren't going to take very long, because they're mostly stuff we're starting to work on now and extending into the future, is what processes shape passive galaxies that were already present 8 billion years ago? The things that were already dead in these kind of clusters that I was just looking at. What made those things dead? What turned off their star formation? And then later, where around clusters does the star formation shut off? Right at the cluster boundary, way outside the cluster boundary? So let's look at this first. These are questions that we're trying to answer with this large Gemini observation program called GoGreen, the Gemini Observations of Rich Early Environments, subtitled, It's Time to Care About the Environment. That's the title of the proposal. And this is a large program led by Michael Balog at University of Waterloo. I'm in charge of the imaging component of this. I spent a lot of time on my sabbatical working on this program. And we're observing clusters now all the way back to 9 billion years in the past. Their projected evolution is given by these tracks here in this plane of redshift, time, and halo mass. And you can see that they're going to turn in to these samples of kind of intermediate redshift. These are the EDIS clusters, the ones that I was showing all the results on previously. So we have this really well-matched evolutionary sample of clusters in the near to mid-range universe and those in the distant universe that are the potential progenitors. And we're getting a lot of spectroscopy using this telescope right here, the Gemini North and Gemini South telescope. That's on Mauna Kea in Hawaii. It's an 8-meter diameter telescope. Looks like that when you're actually at the telescope. That's an 8-meter diameter mirror. It's about that thick, so it doesn't support its own weight. It's supported by a bunch of actuators below it. The whole sides of the dome open up to allow smooth airflow through the telescope. And we're conducting this 4-year, 440-hour observational campaign with these telescopes. It's the largest program executed on these telescopes, which are the US's flagship publicly available astronomical observatory. And our goals are to measure how fast star formation gets quenched, what halo mass that works at, what is the halo stellar content and how does that evolve as a function of time, what are the substructure and dynamics of galaxies in these halos. And then also we're going to get tons of spectra of things that aren't in the clusters. So we're going extremely faint, 15-hour exposures with an 8-meter telescope on every galaxy. And so we're going to get this amazing spectroscopic sample of non-cluster galaxies that will be the best spectroscopic sample that exists at these distances. So some of the things we can do, we can look at the quiescent fraction of galaxies as a function of stellar mass. So these data points here are things that already exist, right? But only out to a redshift of 1.2. This green is the predicted performance of our survey all the way out to a redshift of 1.5 and down to a larger stellar mass. So for example, a lower stellar mass. So this is the high redshift bin of this other survey that already exists. It only goes down to here in stellar mass. We're going to get equivalent precision, but a factor, 0.8 dex lower than stellar mass. And these 3 lines here are model predictions for how this should behave with stellar mass. For different models with very different assumptions about how galaxies quench in clusters. Some of them, like this blue line, just say that galaxies fall into clusters, they stick around for a little bit, and then boom, they quench. And they don't actually say what happens. It's a purely empirically driven model. These other two, this red one and black one, actually try and include the physics at some level, and they get totally different predictions, right? So we clearly can distinguish among these with our data. You can also look at how the predicted data in green behaves in terms of this quiescent fraction as a function of radius from the cluster center. This is megaparsecs, which is 3.26 million light years. And again, you can see very different predictions for these models for this radial behavior. So this project will hopefully let us understand what are the quenching processes that put the passive galaxies in the clusters that we study when we look at intermediate redshift ones. The second element is where around clusters is star formation shut off. This is something my student Justin Mann's been working on a lot and something he'll be working on for his thesis. So we can look at the star-forming fraction of galaxies around clusters. Right? So it's the fraction of galaxies forming stars above some certain threshold. In the nearby universe, this is not stuff I did, but it's similar to stuff I did in 2010, but now with much better signal to noise. These are field galaxies, and these are cluster galaxies. Right? So this is the projected radius in terms of what people nominally consider R200 as the characteristic size of clusters. And you can see even out to 2 times the virial radius, you are still well below the field galaxy star-forming fraction. So something's happening well outside of a cluster that causes galaxies to stop forming stars. But this isn't surprising when you actually look at clusters. This treats clusters like spherical cows, right? It says all you have to do is go out in radius and you add up, you just characterize it by this one simple parameter. But this is the Virgo cluster, the nearest cluster to our galaxy. This is recessional velocity, which maps the distance when if you ignore peculiar motions. Things at the same recessional velocity should have roughly the same distance. It looks kind of like a mess. That's the Virgo cluster. You can already start seeing features like this feature, this feature, this feature, this feature, this feature. Galaxies at coherent velocities, all kind of in lines going away from the cluster. I can just look at one small velocity range, and you could start seeing filaments here and here and here. So and if you actually plop down a circle and said, I'm going to use this as my proxy of the density around the cluster, you would get the answer totally wrong because you're mixing huge range in densities from the filaments and groups to the field. And indeed, as you go out in redshift, the fraction of your volume that's occupied by dense regions drops because of purely geometrical effects. Right? because all the galaxies are concentrated in these filaments. So we started about 2 years ago, and have been doing a lot of work last year, trying to understand galaxies along these filamentary structures. We're going to be using, hopefully, the KU Phillips Claude Telescope 1.25 meter to image the ionized gas around these galaxies. We're going to be we already have gotten a bunch of molecular gas observations and detect many galaxies along these filaments to understand the gas depletion processes. We can also try and connect the galaxies outside clusters to the ones inside clusters over cosmic time. So these aren't data, these are simulations, but we've simulated how they would be observed if you could select galaxies in real redshift surveys. These are just 3 example clusters, 5 billion years in the past, from a dark matter simulation where galaxies have been put in post-processing using kind of physical prescriptions for how galaxies grow. But even without that, you don't really care. What these color coding is telling you, anything that's blue or red are things that will be in the cluster in the present universe. And the canonical radius of a cluster at these redshifts is like a megaparsec. So things all the way out there will enter the cluster at low redshift. So if you want to figure out how cluster galaxies evolve, you can't just study the centers of clusters like we've been doing for 15 years, because we've been limited by technology, by telescopes. You have to follow the galaxies from the outskirts at high redshift to the inner parts at low redshift. And this is something we're doing right now. Again, stuff that Justin's going to be working on for his thesis. We actually can already observe some of these filaments at high redshift. This is a map around the cluster 5 billion light years away, but this time a real map where that color scale tells me the density of galaxies. And there's a cluster right down there. That's R200, the virial radius. And you can see this beautiful filament that comes out of that cluster of galaxies. We're currently getting spectra of a lot of galaxies in these filaments. Right? These are brighter galaxies, these red ones. To actually find the filaments, you have to go to much fainter galaxies. And so this is like a huge observational investment, right? Because you can't just point at one spot. You have to map the sky. You have to use big telescopes. You have to expose for a long time. And you have to get lots of imaging data and spectroscopic data. So it's a large international program with a lot of time and energy being invested. And our hope is to be able to map galaxy evolution along this structure here, for example, and in other clusters as well, and compare it to things in these low-density regions. We already have some preliminary results on this, and I've only got a few slides left. These are now 2 different clusters with that similar data that I just showed you, where we've split them up into field, filament, and groups and clusters, color-coded by their mass. So we've tried to encode for some kind of intrinsic property that could control for intrinsic quenching. So in both of these clusters, and there is variation between them, but in both clusters and at a fixed stellar mass, as you go from the filaments to the field to the filaments to the groups and clusters, you increase your fraction of quenched galaxies. And the filaments already give you a significant enhancement, especially in the lower mass bins. So we think we can now start separating this nature versus nurture. We can control for individual parameters, like intrinsic parameters. We can trace galaxies over their full range of environments. Right? We can follow them over time as they migrate from one environment to another environment. And we can get the data we need to understand this. We can also self-consistently compare with the theoretical models. This is a plot of the fraction of galaxies forming stars above a certain rate for different models. Right? So the black ones are all the galaxies you would observe in a given slice, and the red ones are the ones that are actually in the cluster at a given redshift, so in a distant redshift. This is the same observation now, but for the data, stuff that Justin's doing. And what you can see is that here, just look at the star-forming fractions. They're a few percent. These are like 9%, 8%. So there's a difference already between the total fraction of star-forming galaxies and the data in the models. Again, pointing out that the models aren't properly reproducing the properties of the star-forming galaxies. Gabriele De Lucia is one of our close collaborators. He's kind of one of the world experts in semi-analytic modeling that is used to make these predictions. So she's working with us to kind of do this self-consistent comparison. So, as my final slide, low-mass galaxies are quenched later than high-mass galaxies. Merging may be amplified in clusters. We're trying now to understand how we can understand the merging history, the morphological transformation of galaxies, and their star formation quenching, and figure out the relative timing of these two things. It's an ongoing project. but we're chipping away at it. And we have a whole branch of new surveys that are allowing us to understand both how galaxies enter from the outskirts of clusters to their cores and are affected, and how how the galaxies and clusters were formed 10 billion years ago. That's it. Thank you very much.
Questions? Gopi?
So the simulations that you presented, I'm assuming they assume dark matter halos that have single component dark matter?
Yes. All these simulations assume single component dark matter, and I have no idea how they would change if they didn't. I just don't know.
So I guess what I'm wondering is, we know that there's a problem with single component dark matter. Like, does it match the data that you're studying?
Well, I think that the main, and Misha probably should correct me, the problem with single component dark matter is the small scale structure inside the centers of galaxies, the actual mass distribution in their centers, the abundance of dwarf galaxies, very, very faint galaxies, 10 to the 7, 10 to the 8 solar masses around galaxies like the Milky Way. That's the driver for that discrepancy. The large scale, pure cold dark matter works fantastically for describing the clustering. The disagreement here, I think, is all in the gastrophysics. It's how we implement baryonic cooling, baryonic feedback, star formation. All the baryonic physics is subgrid physics, right? Your resolution, even in the best simulations, is 10 parsecs, 100 parsecs. There's now brand new zoom-in simulations of individual galaxies where they can get down to the parsec scale. But everything that happens below that, how the stars actually form, is put in as prescriptions that then are implemented in the larger simulations. And I think we're still resolution limited there. I shouldn't say we, because I don't do the simulations. But as people go to higher and higher resolution, with more and more realistic star formation prescriptions, they get a better and better match to the detailed properties of galaxies. But those haven't yet been included into these large-scale simulations because it's computationally too intensive.
Yeah, because I guess I was wondering how do different halos impact the galaxy formation, star formation in the galaxy? That's why I was asking.
Okay, so if you have a big halo, one thing that people think is that as the gas falls into that halo, if it shock heats, once it gets above 10,000 degrees, it doesn't cool efficiently anymore. And that mass threshold is around 10 to the 12 solar masses, around where the Milky Way is. Once you get above that mass threshold, it may be that your gas heats up and stays hot for a longer time, which drops your star formation a lot because you just have deprived the rate at which you're pumping in fuel. There are problems with that model, but that's one idea where the halo mass is really the governing thing. All the other ways of cutting off star formation intrinsically involve some kind of black hole feedback, right? So you can turn it off with a big burst of star formation or a big blowout from a black hole, but then keeping it off is a problem, right? Galaxies produce their own gas from mass loss. New gas is falling in all the time. So you need some kind of maintenance mode to keep the star formation off, and that may or may not depend on the halo mass. I think people are really, they think that some kind of AGN feedback is the most likely culprit.
Questions?
It seems like the star formation galaxy cluster is stronger than the star formation galaxy. I'm wondering why.
Why, sorry?
Why the non-star?
Why are there more non-star forming galaxies in clusters than star forming galaxies?
I mean, why the non-star forming galaxy cluster is stronger than the star forming?
I think that's, there's two possibilities. So you got at the heart of the problem. Like, why is it that clusters are dominated by passive galaxies? There are basically there's three possibilities, right? One is that everything is intrinsic quenching, and it's just that the galaxies and clusters tend to be more massive. We know that galaxies and clusters tend to be more massive. There's a bias there. But even for really low mass galaxies, we see the excess. So it can't be different galaxy distributions in the different clusters. It could be that the galaxies and clusters are older. These are the more massive overdensities. They collapsed earlier. We know that their dark matter halos formed earlier. And so it may be that they just have more time to form. The problem with that scenario is that all the studies we've done of the actual quenching process indicate it has to be fast. If it was just that the galaxies were all a little bit older, a little bit more evolved, you would see a lot more intermediate galaxies, things in the process of slowing down their star formation rate. And if you look at the detailed stellar ages of the older galaxies, you find that there's only like a 5 to 10% difference in their stellar ages. It's not a big difference. So the last option is that the environment is actually the thing that's affecting the galaxies, that something about being in the cluster makes you shut off your star formation. And therefore, by construction, those galaxies are more clustered, because it's the dense environments themselves that influence it. Does that answer your question?
Okay. John? So you showed us a lot of qualitative studies, usually with a fraction of some quantity relative to some baseline. And there's many arbitrary cuts, there's many arbitrary classifications. Whether you call the fields or the clusters at 10 to the 11 or 10 to the 12, there's so many qualitative decisions made before you get to cutting a graph that I don't sure know if I even saw a single, two signal.
Well, so
I have a question here.
Well, no, you don't get to ask your question until I address your statement that you don't see any 2 sigma signal. So this is not an arbitrary definition. These are the guide the eye, but this trend exists regardless of how you actually
Field
fit your
filament
data.
and groups are completely arbitrary.
No. The labels are arbitrary. If you actually go to the data and you
What
ask.
is passive? What does it mean to be passive? The fraction is passive.
No, the passive definition is actually quite robust, because galaxies are bimodal in their properties. There is not a continuous distribution. It is 2 populations. There's a population that's on, forming stars, a population that's off. There are very few galaxies, relatively speaking, in between. So you can take a line and draw it, and you can move that line around, you can make it a parabola, and it doesn't change anything, because the split's very clean.
Category by category. My question is that since you are making arbitrary categories, taking ratios, fractions, with many, many discrete arbitrary categories, aren't you just increasing the amount of noise and fluctuations relative to another hypothetical study you might make, where you would let the data as you have it organize itself? Just say, I don't know in advance whether the fraction is interesting for the total number, or whether some linear combination of quantities would show a good correlation. So have you considered that by, what I see is a rather biased and presumptive scientific approach, which you already think you know what's important with passive, active groups, clusters, filaments, fields, and log mass cuts. Maybe you're making a lot of the data that has information that would get lost, taking ratios that increase the noise compared to signal.
So if you do
if you had another data analysis procedure, which was just simply bottom-up data driven, that maybe you'd find more sharp and nice empirical regulation.
Well, if you don't control for everything appropriately, it becomes, so you can try, we haven't done this yet, you could try some multidimensional analysis where you just try and figure out where things lie. We haven't done that, and I think historically just the data has been, no, but let me finish. So what you can do is you can actually do, for example, cumulative distributions of the data, and there you see these result trends popping out as well. For graphical purposes, sometimes it's nice to be able to plot the data in bins. Binning, of course, erases information, and so when we've been able to do it, we've plotted distributions of data and tested the differences of distributions. Some of the fractions, like is it forming stars or not, are purely data-driven fractions. We have data of a certain, that can, for example, this, we can only measure star formation rates down to that level in individual galaxies. Our data doesn't go deeper. This infrared data has a certain depth. So we're forced by the data to make a cut. We can also ask, what's the distribution of galaxies above this cut, for example? We haven't done that because Justin's thesis is just starting. We also can ask, if I have an image of galaxies for which I have no star formation detected at this threshold, I can ask, what is the distribution of marginal detections that reproduces the observed signal? So you start modeling, the few sigma results of each galaxy on the ensemble, right? The problem there is you don't know which galaxy is driving it, but you can model that with bootstrap simulations, for example, Monte Carlos. So these are definitely things that we've explored. Sometimes, though, we use our prior knowledge. We know from other studies that have focused on different areas, because not one survey can do everything. No one survey in astronomy gets to do everything. Some surveys specialize in understanding intrinsic galaxy properties by focusing on galaxies that are not in large density conglomerations. Other galaxies like ours tend to mostly have galaxies in the dense regions, and we're driven by data limitations on getting galaxies in those lower dense regions. We would like to have large samples of all, but we simply can't do it. So what we do is we take studies that show that indeed there is this very strong predictor of internal passivity, which is something like the stellar mass, right? And then we apply that prior knowledge when we try and control for some intrinsic property. We don't have the ability, for example, here to control by anything but mass, because you don't have sizes, for example. That's another thing I didn't talk about. So it's very rich, but the problem is if you start going to other data sets and including all that data in, you start running into big systematic biases, because those data sets may not have the same exact observational selection effects as yourself. So we always have to balance this. It's something we do all the time. Do I want to get better sample size so I can perform more multidimensional analyses, or do I want to keep my systematic errors lower by trying to just stick with my own data? That's a constant battle, and we'll always try different recipes. The binning we do use tends to be stuff that's very physically motivated or very driven by the data. Passive or non-passive is accepted by the entire astronomical community as a very good discriminator. And you see it strikingly in plots like this way back at the beginning. Not the cheese. Here, right? Passive, non-passive, with a big gap in between. You can change where these lines are drawn, but it doesn't make a difference. You can come up with clever ways to isolate these, which we do. It doesn't make a difference. So we've tried testing the sensitivity of these binnings, right? We've tried plotting distributions when we can. I think you're absolutely right that we have to be aware of few sigma effects, because as Jerry Oestreicher said, half of all 3 sigma effects are real, right? So if you have something, which anybody who knows statistics know, that means you don't have a Gaussian distribution. So we have to be aware of these things when we're looking at 3 sigma-ish results to 5 sigma-ish results, right? Or even higher. Once you get above 5, it's hard. But the problem is these are highly intertangled behaviors, and we're constantly in a struggle to gather enough data to be able to test things at a better precision. So in many cases, these are motivations to get more data, to get more precise tests. That was a long answer, but it was an involved question.
I think that we should thank Greg.